Let's look at another triple integral. In this particular example, what we want to do is use the triple integral to actually compute a volume. So I'm going to take this opportunity to introduce a new coordinate system. Even though it's one section early, I think it makes a lot of sense since we've already talked about spherical coordinates in the class. So we want to compute the volume of the solid bounded by the upper hemisphere and the xy plane, z equals 0. So again, you get this type of solid here, that is the upper hemisphere bounded by the xy plane, and we want to find the volume of that. Now clearly, you do have a formula from high school geometry for the volume of a sphere, and we've used other coordinate systems to actually compute the volume of a sphere. But I want to actually kill two birds with one stone with this problem, looking at the Cartesian representation and the spherical coordinate representation. So what we first start out with is our function, that is the ceiling of the solid and also the floor of the solid. So when we actually describe that, we have the following. That is the square root of 64, x runs from what? -8 to 8. And then building, y will run from the negative square root of 64 minus x squared to the positive square root of 64 minus x squared. That just basically forms the area in the xy plane, the blue here. And then of course the actual hemisphere, z will run from what? The xy plane to the positive radical 64 minus the quantity x squared plus y squared. Now, before we move on to the spherical coordinates, let's just look to see what the actual triple integral would look like with the Cartesian. That is basically what we do is we integrate the triple integral dz, dy, dx. That is, this is the volume element with these parameters. So we have, again, the x, -8 to 8. We have the y, the negative radical, to the positive radical, and then we have the z, the 0, to the radical for the hemisphere. So what's interesting about this is that even though this describes exactly what's going on, the integral is very difficult. But in a more friendly coordinate system, namely spherical coordinates, we could actually produce a much simpler integral. So when you think about describing this particular solid with the spherical coordinates, it reminds you of the polar. That is, you know that theta needs to run from 0 to 2 pi, that is to move around to cover the entire disk. And then the actual angle between the positive z-axis and phi will have to run from what? 0 to pi over 2 to cover all of this area. And then, of course, we need to fill out the solid to let the non-negative distance from the origin run from 0 to 8. So this will give a very simple description of the solid here in a way that makes it simple to execute. Now, remembering back at the beginning of the course, we had the x, the y, and the z. That is where we write the x Cartesian coordinate in terms of the spherical coordinates, the y Cartesian coordinate in terms of the spherical coordinates, and the z Cartesian coordinate in terms of the spherical coordinates. And this is what we derived, and that was a fairly simple derivation. Now, if we want to change variables, we need the absolute value of the Jacobian. And this is a computation that we will do that you'll see in your notes. The absolute value here will just be rho square sine phi. So that particular expression will be what we need to execute the change of variables from Cartesian to spherical. So now we can see that all the work has been laid to transform from Cartesian to spherical. So all we have to do is, again, write this expression, rho squared times sine phi, d rho, d phi, d theta. And when we pair these off, theta 0 to 2 pi, phi 0 to pi over 2, and rho 0 to 8. Now what's nice about this particular integral, it's very simple in that all of the limits of integration are constant, so we can just break it up and do these integrals in any order you like. So let's just go ahead and move the d theta integral to the left, and then the phi integral in the middle, and then the rho integral at the end here. All very simple integrals. This integral we've seen many times. That'll just give us 2 pi. And then, of course, the antiderivative of sine is the negative cosine, integrated from 0 to pi over 2. And then, of course, rho squared, that's add 1 divided by the new power, rho cubed, divided by 3. And so now when we actually execute the fundamental theorem, we're going to get cosine pi over 2 minus cosine 0. And then, of course, here we just get, if we factor the 1/3 power, we just get 8 cubed minus 0 cubed. And I'll go ahead and write in the cube for the 0, just to make sure everybody feels comfortable with that. Now, of course, we're pretty much done. This will be 0 minus 1, giving us a negative 1. And then we have the negative 2 pi over 3. And then, of course, 8 cubed is 512. And when we see the negatives absorb, and 2 times 512 is 1024. So the volume of the hemisphere, hemispherical solid, is 1024 pi divided by 3, done in a way that's absolutely reasonable. And I hope this introduction to the spherical in the change of variables has been good for you, because it's very important, and just like polar coordinates and spherical coordinates, it lends much ease to doing certain computations. And we are done.